Hello everyone, good morning, welcome back to COMP526. Hope everyone's doing fine and you enjoyed the bank holiday and had a little break. See what we have today. I have a couple of announcements, so I'll start with those and then come back to the question about the class test 2, which is, well, it's also one on my list here. So there we go. Number one, I sent you a very long email about the exam setup and how the exam will look like. So that was yesterday. I don't expect you to have read that email in detail yet. Please do read this email before the exam approaches. I know that's still some time left before this becomes imminent, but I wanted to set this, wanted to have this settled well in advance. So that email is very long. It contains a lot of things. The important part is I set up a mock exam on Canvas, which looks exactly like the final exam, except that I didn't show the actual questions. That would have made the final exam a bit easier, but I guess also not quite as interesting. So instead, I put in replacement questions. The first 6 questions are actual ones. They could have occurred in this exam, or some of them I took from old exams. So these are real questions. They could have occurred in exactly that way on the final exam. These ones won't, obviously, but it should get you, it should give you a good feeling for what the questions might look like. And the second big thing why I created this mock exam and put it out early is you can test your technology setup. By the way, we know our exam will be May 28, I think, the final exam. So that schedule has been released. You will have received a separate email from the student experience team about that. So on that day, you pick a 3.5-hour slot to do our exam. You can start at any point in time, but then you have to finish before the next day, 9 a.m. UK time. It's on Canvas, and the mock exam shows you exactly how it will look like. It's a little different from other Canvas exams. It's not a multiple choice only exam. Therefore, I set it up slightly differently than some of the other exams. But please check out the mock exam. I don't want people to get into technology trouble that comes from not understanding how the system works if they haven't seen the mock exam. I will get very mad at you. So please give it a try and make use of the questions that are in there for practicing. I put it out already. We're well ahead of time with that, but I thought it doesn't hurt. Okay, the next point on the list is the end of module survey. We're not quite at the end of the module, so I decided we will run this next week in the Tuesday session. I'll leave some time for you to fill this out and send you an email on the spot. If you feel like you want to do it already, that's fine too. The survey is open since yesterday, and you have till end of next week. All right. The upcoming deadlines, you know, you always find this on Canvas as well. But for now, let's look at the programming puzzle 2. So I guess half of you haven't really started looking at it. Please do that. For the following reason, it's a creative task and you will need some time to think about it, even if that's just at the back of your mind. So definitely have a look at the task and read through it, what you should do, and make sure you understand what you're supposed to do, because then you can also have your questions on CampusWire answered. I will not answer questions on the setup, what the problem is all about the day before the assignment is due. I don't want you to postpone it to the very last moment. please have a look at this, the latest this week, better today, and give it a quick thought. Then there's a few people who had a brief look. That's the other half, mostly. Okay, so it doesn't make much sense to talk about this today. Let's do the following. I'll ask the same question again tomorrow. And if we have a peak on this point, then maybe it makes sense to talk a little bit about it. Otherwise, you kind of miss the chance. The next time we see each other is then the day before the assessment is due. I think that's a bit late to really talk about what the problem is about. So please have a look at it. I know there's other assignments and deadlines piling up. I'm not sure what to do about that, really. It's towards the end of the term. I think many people have their assignments due. Okay, caffeinated for the rest of the class. With that, I think I'm through with what I wanted to say. If you have questions, please pop them in the Q&A, as always, and then we'll continue. Yeah, as always, please use CampusWire. I'd love to see more questions coming up there. I doubt that my explanations in class are so brilliant that everything's totally clear and no questions are left. That just seems unlikely from experience. So please, if you stumble upon anything, whether it's organizational or on the material, please put it on CampusWire. That's what it's there for, and it will encourage others to either answer or say, yeah, I actually have the same question. Okay, with that, let's go back, unless you have questions. There are more questions. I'm happy to take them. Otherwise, let's continue with Unit 8. We were discussing Hamming codes, and I had to stop right at the point when it says, now let's see what the solution is. I want to briefly recap what the setup, what the problem was. We talked about parity bits. So you can add a single bit to a block of bits, and that's enough to detect a single bit error, but you cannot correct it. I asked this question. Shall we bring up the results again, just for the fun of it? So this was the detection, but I really want the next one. Okay, so this was again about the parity bit. We've already talked about that. What's interesting for today is this one. So here are just the results from last time again. If you want to correct a single bit error and you have a block of 100 bits, how many extra bits do we need to do that? And there were answers on a wide range, say. And we'll see today what the correct solution for this is. And that's where we left off. We saw a very simple code. We saw a very simple code where you just duplicate every bit 3 times. That's very space inefficient, but it allows you to correct any 1-bit error within these 3 bits by just taking the majority. But an overhead of 200% is too much. We can't afford that. We don't want to afford that. And the claim is we can do it with roughly 11% in this scenario. And that's also, I think that should also work out to be roughly 11% for the 100 bits. So 11 extra bits should be roughly it. I see, it should be a few less actually. So this is what's that block size? Okay, we'll come to it. Doing the calculations in my head may not be my strongest point. So this is where we left off. We left off last time here announcing that there are error correcting codes that don't have this massive 200% overhead of the duplication code, the simple one where we send each bit 3 times instead of just once. So the announcement was that we can get this with 11% of overhead for a reasonable block size instead of 200. I'm sure you are all curious to find out how that should work. So here it goes. The conceptual idea is we want to use parity bits, not just one, that can't be enough, but several of them. And we want to somehow use the parity bits to locate errors. If we have a single bit error, then it's basically enough to know where the bit error occurred. Then we can just reverse the flip it again, and that undoes the mistake. The only question is, how do we use parity bits in a smart way to achieve that? And that seems not quite obvious how to do. But it turns out this is entirely possible with the following setup. I'll go through this in a second. I just want to point out this one here. We cannot rely on the bit flip to occur in the data bits. It can also be one of the parity bits, and we have to live and cope with that just as well. So without further ado, and without motivating this on that side of things much more, here is essentially the solution. We use 7 bits in this example. So these are these 7 bits. But they are not allowed to be arbitrary bit patterns. We want that whenever we have 7 bits, B1 up to B7, that these checking bits, C2, C1, and C0, are all, well, 0 modulo 2, the XOR of all those bits is always 0. And how does that work? Well, the blue checking bit just takes the first 4 position and takes their parity. Remember, taking XOR, first of all, it's associative, so you can do this in any order you want, as long as you're grouping the same bits at the end. And XOR has the feature that if you XOR a certain number of bits together, the result is exactly the parity. It's 0 if the number of ones in that collection was even, and it's 1 if the number of ones was odd. So C1 does that for the first 4 bits, the highest 4 bits. C2, the green one, does it for the first 2 plus these, counting from below, it's these 2 and these 2. And then we have the magenta one, which does it for every other bit starting from the outermost. That looks like a very curious pattern. What you might already see is I wrote here some bit strings, and you might be able to figure out what the pattern with those is. But let's first of all just take this as a given. So we have 7 bits, and we enforce that certain subsets of bits have even parity. That means certain bit strings are no longer possible. A first observation, if no error occurs, if all 7 bits are correct, we can find out, we can check for this by computing the checking bits. And if these are all 0, then that's our signal. That's what we use to mean no error has occurred. And let's just observe what happens if we flip 1 bit. Let me see. I want to do an example for this first. Let's say we start with a combination of bits that has the proper parity. And then we flip, say, B3. Okay. So this one's different now. This one used to be 1, say, and now it's 0. What that means is that both the magenta and the green checking bit will also flip its parity. C2 is not affected because it only takes the blue positions here, and B3 is none of these, so there's no change in parity. But C0 and C1, they both flip to 1 because they were even before, and now we flip a single bit that must change the parity. And now notice that if you write 0, 1, 1, that is exactly writing the number 3 in binary. And if you take all the other numbers 1 through 7, then you see the colors or which checking bits a certain bit is taking part in is exactly encoding the index in binary. So that's what's also written on the slide now. In general, this holds for any of these bits. If the jth bit is flipped, that means we get if the ith bit is flipped, sorry, then we get a representation that the checking bits, the jth checking bit is 1 now, indicates a mistake if the jth bit in the binary representation of the index I is 1, the index that we flipped. Okay. And that is the essence of the Hamming code. We use this set of constraints here to enforce a certain structure on these 7 bits that allow us to find out if an error happened, and if so, where. Because whenever some mistake happens, the checking bits essentially tell us where was the bit flip. It's pretty ingenious and also quite simple. But if you start from scratch thinking about this, I find it intriguing that it's possible to do this very simple trick to find out where the mistake had happened. So the checking bits simply encode the position of the 1-bit error, and we allow 0 to signal no error. That's why the bits are numbered from 1 to 7 here conveniently, so that the 0 as a code for the checking bits can indicate no error has happened. Let's now turn this into an actual code. So far we've said there's these 7 bits, they just fall from the sky and they magically happen to satisfy these constraints. That's not how coding works. We start with some message bits and we want to add some extra bits of redundancy to turn that into an error correcting code. How can we do this for the 7-bit constraint, the constraint 7 bits that we did here? The core observation is that 4 of these bits, namely those ones, they only occur in a single checking bit, right? The magenta, blue, and green one. And that means we can define these based on the rest. So we can keep those, the bits at these indices 3, 5, 6, and 7. We can treat them as the input and then choose B4, B2, and B1 so that the checking bits are all 0. That's the idea. And it nicely works out that these are the powers of 2. So their binary representation has a single 1. That's exactly why that is the case. And you might already see how to generalize this picture. But for now, we'll stick to the 4 plus 3 Hamming code, where we have 7 bits in total. 3 are used as parity bits. So the 4 remaining ones are the message. So if we start with a message of arbitrary 4 bits, we take those 4 bits and put them in order into the positions that are not powers of 2, whose index is not a power of 2. And then we compute the other, the remaining bits. So I called these here P1 to P2, P0 to P2, the parity bits. but they're really just chosen so that the C's are 0. Okay, so we have 4 different types of bits now. Just to get that picture clear, let me repeat that part. In the world above here, in the upper world, we have a 7-bit string, that's the B's, this one. And we have the checking bits. And these are just, the bits come from somewhere, and I can compute the checking bits, and then either I say, I like this code, no error occurred, or some error occurred and I can tell you where. That's just, that's the mathematician's point of view. It's a definition, and I can say something about it, but this is not an algorithm. The bottom part, this one here, we have the D bits, that's the input, and we have the P bits, that's the output. We compute the P's from the D's shown by this formula. So we compute the parity of certain data bits. And it's just another way of saying, if you take the D bits and the P bits and you interleave them as shown and treat them as the B bits, and then compute the C bits will be 0. Okay? So that's maybe a more complicated way of saying what's written here. The algorithm for encoding in Hamming codes is very simple. You take your 4 bits of the message, you put them in the right positions for the B's, and you compute the P's with that formula and put them at the remaining positions. That will automatically make your C 0. That's the encoding step. That gets from a 4-bit message, it turns into a, how can I do 7? 7-bit, into a 7-bit block, a block code. That's what you transmit over your unreliable communication channel. And that channel might flip a bit, or it might not flip a bit. And then we receive some bits and have to decode it. So that's what we will have to do next. First, we've only seen how can I produce the code. Now I have to also get back to decoding this. Okay, I forgot this last. I forgot that I have this interleaving step explicitly here. It's also in the picture. We talked about this. How can we decode this? So that's the second algorithmic part is you're given this encoding basically was from the bottom world to the top world. We got the D's, we computed the P's, and therefore we computed the B's. And now we try to go the other way around. We receive from our channel these bits, B, the 7 bits, and we don't know what happened. But we can compute C just using the formula from above and using the XORs. And then we know if C is 0, probably no error has occurred. Now, to be precise, the statement here is that no detectable error has occurred. Now, of course, that's important to note because it can happen that more than 1 bit flips. If the communication is really unreliable, we could have that situation. But no code can possibly detect if your channel completely randomly flips the bits. There's no way you can decode this. This is something you can prove. So we'll assume again that bit flips only happen rarely. So again, if C is 0, no detectable error occurred, and we'll talk at the end of this subsection a bit about what that means. What are the detectable errors? Otherwise, if your C is not 0, you know exactly which of the bits was twisted, and so you just flip that again, undo the mistake, and that's it. Then you're back to a code word that has C0, so it's a valid code for the Hamming code. And then you just have to take out the appropriate subpositions. That's the message bits from your Hamming code. That's the decoding step. It's fairly simple and fairly easy to compute. So this is an efficient algorithm. Just pointing this out because I'll come back to this question of how to decode. If you have any questions so far, that would be the right moment to ask them. We've seen how to encode, we've seen how to decode. Now I'd like to move on to discuss the properties of this error correcting code. So I'll give you a second for asking your questions. But if you don't have one, if you don't have any questions, then we'll move on. It doesn't look like you have pressing questions at the moment. So let me move on to this nice question. If you remember from the lower bound chapter, we talked about code distance. This is something, it was last week. It would have been nicer to have this in one session, then memories would have been fresher. But please head over to Slido. What I did is I just set this up as a tag cloud answer. So again, you can just freely type a number, but really the answer should be just a number. And code distance, that was this notion of Hamming distance. If you take any two code words that are valid in the code, what is the Hamming distance between those code words? And that had to do with the ability of a code to detect and correct a certain number of flip bits. I'll give you a second to answer this, but yeah, I think we should really get 20 votes before we move on, because this is an important point, and it also is a great way to connect to the maybe more theoretical lower bound section. Okay, I see answers slowly coming in. I think we can do at least 20. There were 23 votes for the opening question about the programming puzzle, which maybe I didn't leave open very long, so maybe a few people missed it. But we should be able to get 20. If you have no idea, just, I don't know, type no idea. That's also fine. You might want to go back and check the definition of code distance. That might be something I could do. Let me try that for you. But I don't want to reveal the answer. Okay, I'll really would like to see a few more results on the poll. Time to wake up, guys. If you have no idea, type no idea. That's fine. Don't be ashamed. I know it was last week when we talked about this, and this came out of the blue now. Come on, you can do this. Well, are we really so few people today? I can see you now. We've seen there's at least 17 people in the stream. So we should at least get the 17. And don't you turn off the YouTube stream now. Oh, it actually dropped to 16. I scared someone away by saying this. Okay, so let's keep it with the 16. Here are the results. And you see some peak for 3. That's good. There's also a lot of other answers. Okay, let me lock this in now. Here's the slide from last week when we discussed this. First of all, remember the distance of a code was defined like this. You take any two code words. Maybe let me make it a bit bigger. You take any two code words, X and Y. So, and code words, again, is everything you can get by taking a valid message and encoding it without any mistakes. Okay, this is all the n-bit strings you can actually get if you take if you take a message, an arbitrary message, apply the code, and don't do any mistakes yet. That's all the code words that we get. So in our Hamming code, you take your 4-bit message, you add the 3 parity bits, and that's it. That's your code word. Whenever C is 0, the checking bits are 0. And then what's the distance? How many bits change if you change one message bit? Well, it turns out every message bit is part of all 3 checking bits. So in general, these all change, but some might flip twice. We get the same. We get a. Okay, this is if you flip several bits in the message, you might flip only 1 bit in the parity bits, but it turns out 3 is the right answer. Okay. And it's good to have that slide here because we discussed about what the implications of a certain code distance are for the detection and correction of mistakes. So first of all, if D is 3, that means we can at most hope to detect 2-bit errors. There's no way we can detect 3-bit errors because that might have been already taking us to the next valid code word. And we can correct at most that number of bits. So if you insert 3, that works out to 1. And that's what Hamming codes promise to achieve. Okay. So let's just, for the record, put the number here. So 3 is the right answer. And well, there are many ways to work this out. Let's also recall the lower bound that we had for Hamming codes, or for general codes. We had this lower bound on how big the distance can be with a certain combination of message length and block length. So here we have 2 to the 4 different valid code words, because that's the number of messages. We have 4 bits for the message, 2 to the 4 different combinations. And we create 7-bit code words, okay? Any of these 7-bit errors is corrected towards a valid code word. If we change any of the 7 bits, then our checking bits indicate which one was flipped, and we can reverse that flip, okay? What that means for a single code word is that it covers, it is reached by 8 different 7-bit strings. When I receive 7 arbitrary bits, there are always 8 combinations of 7-bit strings that map to each code word. Namely 1 where the code word itself is sent, and 7 combinations of changing a single bit. Okay? Now if you multiply these two things, we have so many code words and each covers so many 7-bit strings, you obtain exactly all 7-bit strings. So Hamming codes entirely cover the 7-bit strings. It never happens that you receive a code and you think you don't know what to do with it. Whenever you receive a 7-bit string, you will correct either 1-bit error, a flip bit, or you will declare there is no error. Okay? That means we can always correct a single bit error. That's great. The distance works out to be 3. And we can briefly think about what happens to 2-bit errors. We can definitely not correct them. That's what the lower bound, the theory, already tells us. But maybe we can detect 2-bit errors. The problem here is, so if 2 bits are flipped, we definitely notice that something has happened, because the checking bits cannot be all 0 if we flipped 2 bits. But the decoder will eagerly mistake this 2-bit error as a 1-bit error from a different code word and correct that 1-bit error, taking us actually further away from the original message. So in this case, Hamming codes fall short of achieving everything that the theory predicts might be possible. They can always correct 1-bit errors, but they cannot detect 2-bit errors. They can only detect and correct 1-bit errors, that's obvious. But if 2 bits are flipped, you correct that in another direction. There is a small variation. If you add another extra bit, another parity bit for the entire block, you can actually detect all 2-bit errors, but then you also use 1 extra bit. So in a sense, you don't get both with Hamming codes. You don't get the exact coverage of the 7-bit strings of the entire space of possible bit strings, and the best possible detection. So that's just a minor remark. Our 4+3 Hamming code, this will be the variant that we discussed in detail, encoding and decoding. And this addition might be called 4+4 or 4+3+1, I don't know. This is only for your interest, but it will not play a further role in this class. Now we've seen this example of the 4+3 Hamming code. You can generalize the same recipe to larger messages or larger blocks. And the general recipe is as follows. It only ever works if your desired block length is a power of 2 minus 1. In our case, we had L equals 3, which works out to N equals 7. That's 8 minus 1. And you can generalize this code to other powers. So you can choose L. That's a parameter for you to pick. You use the L bits as parity check. As parity bits as part of the making the checking constraints 0. And you use exactly those that are at a power of 2, because then their binary representation is only a single 1. And so you can define them based on the other bits. And the other bits, well, that's N minus L in the general case, all that you didn't take. And that's pretty much it. So, I mean, you generalize the checking and parity bit formulas from what I've shown. Basically, you take this binary representation of every index in your block, and for every position in the binary representation, you have 1 checking bit. So just to make this very clear, let's go back to this again. This picture here, if we have 7 bits in total, I can represent all those numbers with 3 bits in binary, or 3 digits in binary. And that means I have 3 checking constraints, 3 checking bits. And the last one takes the last bit in the binary representation. Whenever that is a 1, I include that bit into my constraint. And notice that these are all the odd numbers, because the odd numbers have a 1 in the binary representation at the last position. Then I have the next position is whenever the second bit is a 1, and that happens to be those 4 numbers. And finally, the last one for the most significant digit is the upper half of the code. And you can generalize this. If you have 15 bits instead of 7, you have a 4th position in the front. So you would use a 4th constraint for the new most significant digit. That's how you generalize this. And now we have the parameters N and L to play with. Here's my example from before. If we want this 11% overhead, what we can do is choose L equals 7. Then we can encode 64 bits. That's 1 word of memory in our usual architectures, 8 bytes. So you can encode that as 1 block together, and any single bit error in 1 word of memory is then correctable. Now, you might notice that 2 to the 7 minus 7, 2 to the 7 minus 1 minus 7, doesn't quite work out to 64. In fact, we waste a lot of bits here because 64 is just about too big for choosing L equals 6. We could actually use the same Hamming code, could use 120 data bits, but we can just leave some of them unused and pretend they're all 0. But the important point is we use seven checking bits, 7 parity bits on top of the data. So 7 out of 64 hopefully works out to be roughly 11%. Okay. And if you want less space overhead, you just make your L bigger, and then the space overhead becomes smaller. So in summary, Hamming codes are quite simple. They're also very efficient to realize both in hardware or software. And the overhead they introduce is really, really low, especially if you make the block size a little bit bigger than the 7-bit example we've seen. Also, Hamming codes are in a certain way best possible. Well, in the coding theory literature, these are called perfect codes because they of this property that they cover exactly the entire space, and they have not just the maximal distance between code words is the minimal distance between code words is 3. It's also basically true that code words, there's no gap left. Not all code words have difference 3, but you basically have all possible code words covering the space perfectly. It's probably the best way to say it. And this is the general pattern, right? This is your message length, and this is the number of parity bits. If we want this, we cannot. So because these Hamming codes are perfect, it's not possible to go with fewer bits. You won't be able to use fewer bits for this scenario. So you cannot improve on Hamming codes if the message length is like this. The formula from here, and well, we've seen the example for 4 in detail. We've used the example with 120 bits where we just used 64 of it in the previous example with the 11-bit overhead. You can take all these other numbers. That's message lengths, and we want to correct 1-bit errors only. If these two things are what you want, then Hamming codes are the perfect solution, and there's no possibility to improve upon those. But this is a big but. If either of these conditions is not exactly describing your situation, the situation is not so clear. For example, suppose we want to protect these 64 bits and not 120 against 1-bit errors. Maybe there's a much smarter code than the Hamming code that does it with just 6 parity checks. That might be possible because for these message lengths, it doesn't nicely cover the space. The Hamming code doesn't nicely cover the space. It overlaps. And so that is a bit wasteful. And in fact, this is a fairly open research area. Designing good error-correcting codes is still a challenge that's ongoing. And there's some interesting theory behind this that I don't want to go into, but I want to just mention the main result, the gist of it. Information theory, the same thing we used with entropy in the compression chapter. There's a corresponding theory for error-correcting codes and communication over noisy channels. And the theory basically tells you if you design a code by randomly choosing code words. So you take all possible, say, 64-bit strings, and you choose a subset of those as code words and come up with some way of encoding and decoding. If you do this randomly, it almost always works out to have very good properties in the sense that your distance will be good and you can use this as an efficient code, filling the gaps that are left by Hamming codes when the parameters don't work out so nicely. But there's a big problem with these random codes. They both basically need a full lookup table to encode and decode. For Hamming codes, we had this nice little trick that you compute a few parity checks, and then the checking bits tell you exactly where the bit flip was. You just reverse that and you're done. That was for decoding. That was very, very quick and easy. These general random codes don't have that, and it's not known how to construct in general codes that both have good distance properties and are efficient to decode. So this is where still a lot of ingenuity and tricks are used. And there's still a bit gap between the codes that we can use in practice because they're fast enough to use in practice and the theoretical possibility. It's a large gap in that the currently used practical methods are not as good as they might be. The theory predicts there are better codes out there, but they still have to be found. With that little outlook, I want to conclude this Unit 8 on error correcting codes. We've seen a few lower bounds, a little glimpse of the theory behind this, and we've seen the Hamming codes, a very nice little example where everything works out nicely. They're clean, they're efficient, but unfortunately they only work for a small subset of the bigger task where you want to have a code that works with a given message length and a given guarantee of how many bits you want to correct. And that is still an unsolved open problem. Okay, that's the end of Unit 8. This is a brilliant time to take a little break. So let's do that before I continue talking. So this time I have to check the time precisely that I don't again announce nonsense. Okay, let's continue at 11:54. That's 5 minutes. Double check. Yep, looks good. Okay. So that's a 5-minute break for you guys, and then we'll swap gears and go to an entirely different topic, but equally enjoyable, I think. If in the meantime you have any questions about the previous about this topic, anything before that, or any organizational questions, feel free to put them in the Q&A, and I'll see you in 5 minutes. That's the one. Hi everyone. Break's almost over. 3 more seconds. You had tons of questions, like none. That's great. That probably just means that you liked this error correction chapter very much, and it was easy to follow. Well, let's just close this, and we'll go to a very, very different topic. This last unit is a little different from the ones previously. It's a bit closer to actual research. It's also a little bit more advanced material, so that's why I think I decided that we don't do this for the exam. So this is more of well, for your interest or as an enhancement. And well, just enjoy the show, I guess, is what I'm saying. That's very nice. One comment is that you don't want this module to end. It went too fast. I take this in the positive spin that you just enjoyed it and not that I went way too fast. It's good to hear that you enjoyed it, and I hope that this is just what you meant. I enjoyed it too, even though it's a bit different. I would have enjoyed seeing you more and interacting with you a bit more more substantially than through our little polls and the little chats after class when everyone's in a rush. But that's how far we got. Well, if you liked it, if you feel this style is more appropriate than other forms of teaching, let us know in the survey. I think that's the main part. I did put effort into making it nice and fun, but not everything works. So, well, whatever feedback you have, next Tuesday is a good time to talk about that. So this last unit is basically for your enjoyment. It's another really nice black box that we left, and I want to open this now and show you what's inside, and that will keep us busy for the rest of this week. I think we should actually finish it this week if I stop talking and get going with it eventually. Okay, enough beating around the bush. So if you don't get every last piece of disclaimer, if you don't get every detail of this unit, don't feel too bad. This is really much more advanced material than the previous units. And hence again, I don't plan to ask questions about this material in detail in any of the exams or assessments. But I hope that many of you will enjoy it nevertheless, or even more. So this is about range minimum queries. In this last unit of COMP526, I want to talk about the range minimum problem. A very fundamental data structures problem that both has beautiful solutions, and it also is the missing piece that we left open in Unit 6 about the text indexing application of longest common extensions. And so this is a very nice way to wrap up this class. It will be a little bit more advanced material, so get well caffeinated, definitely for the next session. We'll start slowly, and I'll warn you when I expect that you will find some of the material tough to digest at the first encounter. So let's get going with this one. What is this about? I'll start with a little bit of an introduction. What is this problem? What's this weird name coming from? My favorite subsection title, I won't read it out or tell you what the abbreviations mean by right now. And then we'll look at solutions for this range minimum problem. First, the simple ones that are fairly easy to understand and come up with. And then in the last two sections, we'll go to the state-of-the-art solution. That's also, well, it's best possible for obvious reasons, because it's basically the time you need to read the input. And well, we'll see what's behind this last subsection then next time. All right, what is the range minimum problem? The range minimum problem, or RMQ problem, for range minimum queries is the following simple problem on an array. You're given an array of numbers. Well, it can be any comparable items. So anything you can order is actually fine. We'll use numbers in the example because these are nice and simple, but it could be strings, it could be whatever object you define an ordering relation on. The array is static, so that means it doesn't change. And the goal is to find the minimum in a range. It's a very, very simple question. Here's a range in an array, and you can find the minimum. Well, you just walk through it, and you find 2 is actually smaller than all the others, or at least there's no smaller one, no strictly smaller one. This is trivial to do if you have the time to walk through the array. The scenario that I'm interested in is we are given this array, then we can work on the array in advance, and we know the array doesn't change. So we can pre-process the array, but then we want the queries to be very, very fast. We don't want them to take linear time to scan through the array. We actually want them at the very end. Okay, I don't take that away right now. 2 little details of the definition is we report the index instead of the value. That's a minor thing because you can always look in the array. So if I say RMQ of 7 and 15 is 10, what that means is the range that stretches from 7 to 15, both inclusive, has a minimum at position 10. Okay, I don't report the 2, I report the index. That's just convenient. If you have arbitrary objects, then an index is always quick and fast to return, so you don't have to mess around with any objects. The second thing is we might have ties, like in this example. There's 2 2s. That's the only ones. And the minimum is always take the leftmost occurrence of the smallest element in the range. Okay. So far, so good. I think it's a fairly simple definition, fairly simple problem. You might wonder why people care about it, because it seems so simple that there's not much you can do with it. But not so fast. It's actually very nice. Okay. To see if you're following this, let's do a very quick exercise on this. Where do you have this? Here's the question again. Just remember the 2 nitpicks. We return the leftmost index of a minimum, not anything else. Here's the array again in a little bigger. So this is supposed to be a very simple question. I'm just testing you if you're still awake, basically. And also, of course, we will build on this definition. So it's important that you have this in mind in the right way. Yeah, I'll give you a second, and well, we're not particularly in a rush, so it'd be great if we get the same 17 answers that we had before the break. Well, it seems that a few people left, so maybe 17 will be asking for too much. I guess the announcement when I said this is not on the exam, is that when we when the number of viewers dropped? I'll see a few more. Maybe we can get at least 10 for this question. It's really simple. Don't overthink it. And if you don't, if I was unclear with the definition, say I don't know or didn't understand the problem, that's also fine. I'm happy to repeat that before we move on. Okay, we have 7. Maybe we can get our 10 answers before I show you what you voted. Two more, guys. I know it's getting late in the term. Yep, 9. Okay, I see there's creative answers in there. One more. Great. There we go. And there seems to be a preference for 1. Let's see if that is what we expect. So what does that mean? Okay, range minimum query. So first of all, we have to find the range that this is talking about. That's 1 up to 7. That's not too hard. We'd go from 1 up to 7 and it's inclusive. So that's the range we talk about. We're only looking at this range of the array. So if you wanted, and if that worked well, you could zoom in and say we're only looking at this tiny portion of the array. And now we're looking for the minimum in this range. Well, 4 seems to be the smallest number. It occurs twice. But remember the second nitpick, we always report the first occurrence. So this is where our minimum is. And then the last nitpick, we don't report 4, we report the position. So that's this 1. So 1 is the answer. Good, well done. Let's zoom this again. Okay, good. So everyone's up to speed now, I hope. We find the minimum in the range. We find the leftmost occurrence of that minimum. We return its position. That's our MQ, range min query. All right. Good. So we know what the problem is now. A little bit of commentary around this. We ask for the minimum, so all we really ask for is a comparison-based question. We can do this for arbitrary objects, so the values don't really matter. The only thing that matters is the relative order they appear in the array. In other words, if you give me one array and another array, and the only thing they differ in is the types of objects or the values, but the relative ranking is the same, then every arrangement query will have the same answer. Simple consequence of returning the index and not the value. Now, unlike other algorithms that we talked about, we have more quantities of interest in terms of running time here. We're already used to have time and space. Now we have 2 different times as well. We have the pre-processing time, where that's how much time we take initially to look at the array A and do something smart with it. And we have the query time. That's the time it takes to answer the arrangement queries using the data structure we built in the pre-processing step. A nice result here also, just because, okay, first state what it says. If the pre-processing time is at most P of n, that also means the space usage of the data structure is at most P of n. Simply because suppose the data structure would be bigger, you would at least need the time in the pre-processing step to write down the data structure. So there's no way you can create something bigger than you have time to write it down. You need to write it down, and that takes time. So by bounding the pre-processing time, we automatically bound the space of the data structure. So when I say here 2 main quantities of interest, that's a bit of a lie. We do care a lot about the space. It's just that by bounding the pre-processing time, we automatically get a bound on the space. And that will be in general already enough to have a best possible solution. So a little piece of notation here is this angle brackets, because we have two times. We want to make clear which one is which, so I'll always give the pre-processing first and then the query time, because pre-processing comes before query. That makes sense, I hope. And so we'll just write this as a shorthand notation. Okay. So that's the idea. You're given this array. You can look at it, take your time. You pay for that in the P of n entry, and then once you're done, I'll fire you. I'll fire so many arrangement queries at you potentially, and then how long you take for each, that's the Q of n. So now I want to see just some wild random guesses. What do you think, without knowing the problem, without having really thought about it, without really haven't been given the time to think about it, what do you think, what combination of P and Q is possible to attain? And yeah, I set this up so that you can send multiple answers. So maybe there's different combinations between P and Q. There's a trade-off between pre-processing and query time. That's maybe natural, because there's also a trade-off between time and space. If you write down many more things, maybe the queries get easy. And if you write down nothing, then the queries can't be very fast. So what I'd like to see is this pair of functions, and it really should be 2 theta classes, I think. I didn't write this here, but it would probably make sense to send 2 theta classes, one for pre-processing, one for query. Okay, I meant just something. For example, you could write angle brackets of theta square root n comma theta n to the 5 or so. Obviously, these don't make sense. I don't want to give you any anchor, so that you're free to come up with the answers any way you like it. And I think you can see the answers anyway, so I might as well show this. Okay, you might want to edit the P of n. Yeah, so the 2.5, I mean, this doesn't work for arbitrarily large inputs. We have order n for a couple of things. What's that, pre-processing or query or both? Theta and theta n, that's interesting. Theta n order 1, I should probably highlight this here. That's definitely the best you can possibly get, because you need at least linear time to read the array in the pre-processing step if you want to do anything intelligent. And you need at least constant time to report the answer to arrangement query. So if you could get this theta n theta 1, then we'd be very happy. This one, theta and theta n, is definitely doable, because basically in linear time we can easily solve the arrangement queries even without pre-processing. I'll come back to that in a second. Okay, maybe I'll just leave this open, and doesn't hurt, and we can revisit it a little bit later. In the next subsection, I want to motivate why we study this problem. And maybe that also triggers some thoughts for you, how efficient we want to solve RMQ instances. So here, this is obviously the new abbreviation arrangement queries. You might remember what these are. I won't mention the last. These are the longest common prefixes. That is Unit 6 calling. And you might also remember the longest common extension problem, also Unit 6, and the lowest common ancestor in trees. That's something that we also mentioned in Unit 6, but only in passing. So let's recap a little bit, and I just copied the slides from back then. So if you're a graphically oriented person like myself, you profit from seeing the exact same thing, the same arrangement. So here it is. We talked about the longest common extension problem. You're given a string. My favorite diagram for this was like this. So you have two positions in a string, I and j, and you ask what is the longest piece of text that you can read so that it's the same text if you start at I and at j. So these two things should be the same. And of course, because it's longest, it means if you go to the next position then is not the same. Otherwise, your longest common extension would be one bigger. Well, formally, the longest common extension was the length of this green part, not the string, just another nitpick to make it a little more convenient. And we've already at the time found this connection. There's an obvious connection between LCE and the suffix tree. The longest common extension of two positions is the longest common prefix of two suffixes, namely those starting at those positions. And in the suffix tree, we can find longest common extensions by taking the lowest common ancestor of the leaves for those suffixes and then computing its string depth. So our example back then was this banana ban. And so you could, for example, ask what's the longest common extension starting here and here. That's position 0, 1, 2, 3, 4, 5. So if you execute this, you would find I and j here and here. Their lowest common ancestor is this node, and it has string depth 1. So that would mean I can read one character that is equal, and then the next one is actually already a mismatch. And that works out in our example. Okay. That was what we noticed at the time. And then we found that this longest common extension problem is really useful in doing all sorts of extra clever algorithms on strings using the suffix tree plus this LCE data structure allowed us to solve some other interesting problems. Remember the kangaroo algorithm for finding approximate matches. And at the time I left this, so this is the main point here of this slide. At that point, I told you there is a magic black box for the LCA problem, finding lowest common ancestors in constant time with linear time pre-processing on the tree. And that can solve LCA and hence also LCE in an arbitrary string by using the suffix tree. Okay. So that is a reminder of what LCA and LCE was. The next thing to remember is we also had LCP, the longest common prefix. And that was when we talked about suffix arrays. Not suffix trees, but arrays, suffix arrays. Instead of looking at this LCA question, we can now look at arrays. And so this is nothing we wrote down at the time, but let me illustrate that on an example before we move on. So again, slides from back then. Remember, just for getting the notation in everyone's head again, we had the suffix array L, the leaf array, had the leaves of the suffix tree in sorted order. That is just the suffixes in sorted order. L tells you where does this suffix start, the first, the second, etc. in the sorted order. And we also had R, the rank array, which is the other direction you have for the inverse permutation. You have the starting positions in the text, and then R tells you what is the rank in the sorted list. And so you can use this to go right and left in this picture. Now, what I'm saying here is, suppose we want to find the longest common extension in banana ban. Again, okay, let me write this again. So let's pick the same example. I take this position here, this A and this A, and I want to find from the suffix array, from this suffix tree, I want to find what's the longest common extension. So how much to the left can I walk from this position and get the same string in both cases? We already know it's just the A, but suppose we didn't know. First of all, we find this is position 1 and 5 in the string. So we find positions 1 and 5 in the string here. That's the leaves, banana ban and A ban. Now, the going to the right, I should have probably started here. We know it's position 1 and 5. We can use the rank array to tell us where in the sorted list we find this, namely position 4 and 1. 4 and 1. So here we have A ban and banana ban. Position 1 and 4 in the sorted list. That was the rank. Right, this is just oops, no, this. Okay, now we had this before. My tool crashed again. Let me open it and hope that it can restore the drawing from now. Not clear what it didn't like now, but there we are again. Okay, it's only a couple of things that didn't get stored for whatever reason. Okay, one more time. Where are we? I'm trying to find the longest common extension of anaban and aban, or the longest common extension of these positions 1 and 5 in this string, really. I use the rank array to find where in the sorted list I find these two suffixes. Then when I found them here, I can use the LCP array entries here. Those are the lengths of these overlaps between adjacent suffixes in sorted order. Okay. And now the cool thing is I take this range and find the range minimum query in that range, the smallest value in that range, which is 1. And 1 is also the answer. We have 1 character overlap between these two things. So this is the connection that's spelled out here in big. If I want to find the longest common extension between two positions I and j, I take R, the rank array, to map them into this picture on the right, where I have them in the sorted order. They might flip positions, so 5 becomes 1 and 1 becomes 4. So even though I was less than j, now R of I is bigger than R of j. That's why we use min and max to get those two right. And now I take this as a range here in the LCP array and find the minimum in that range. And because it's a subarray, I can use the range minimum query in the LCP array for that. And here you see I access the LCP array at that index. RMQ returns the index. LCP is the original array. So I find just the smallest value in that green range, and that is my result. Okay. And the reason for that is simply that if this string and this string have anything in common, then all of the strings in between have anything in common, have the same thing in common. And we also have to have one place where this value occurs, where this minimal shared prefix exists. If all of the values in between were bigger, then also the top and this is A band and N band would share more than one character. So I know this this slide was dense and full of somewhat complicated relationships. So let's zoom out even graphically a bit more. The reason here why I repeat this in detail is just to motivate why the range minimum query problem occurs here. It is effectively another way to solve this longest common extension problem, but in the array world, not on trees. This doesn't need the suffix tree anymore. The only thing we need is the inverse suffix array and the LCP array. And we've seen in Unit 6 already how to compute both in linear time with reasonable algorithms that you could implement in, well, say a few days or weeks of concentrated effort. But it's not crazy, not too crazy, and there are implementations available in libraries that one can use. So what does it mean to have RMQ for LCE? We can compute, it's basically what I said, we can compute the inverse suffix array and the LCP array in linear time. So whenever I have a PQ solution for range min queries, that means I have a PQ, same P and Q solution for longest common extensions, right? And so this is probably also the point where we want to go back to this question. To get something interesting here, we really want this one. I essentially claimed in Unit 6 that this is possible. And in this unit, we want to see how to get this optimal theta and theta 1 solution. So maybe that is something to write down here. And again, the comment that this is best possible if I want constant time for the queries, I have to do something at pre-processing time, and doing anything at pre-processing time that's interesting needs to read the array at least once. So this is hard to it's impossible to beat in an interesting way. But we're far from there yet. This is not quite clear how to get, and we'll have to work a bit harder than for any other result in this class, I think, to get to that. Before we finish today, let me discuss the two very simple solutions and how far they get. In this next subsection, I want to discuss the simple solutions to the range min query problem. The sparse arrays will be the final result. For today, we'll leave it just with the most primitive ideas for implementing range min queries. There's two obvious solutions at the extreme ends of a scale, where the scale is from doing nothing at pre-processing time to doing everything at pre-processing time. So one is doing nothing, no pre-processing at all. And whenever someone asks for a minimum in a range, you just find that minimum by walking through the entire range and keeping track of the minimum. That is trivial to do. I'm just listing it here to translate it into our notation. So that is a constant time pre-processing, actually 0, but okay. No pre-processing, constant time pre-processing, linear time query, because the range can be as long as the entire array. That's not very interesting, and it won't get us closer to our final goal. The other extreme end is, well, there's only so many possibilities to ask for ranges. Namely, I and j, I can start at 0, and they have to be sorted. Well, no, it's less than n because we start counting at 0. So there's only n squared solutions for this, n squared choices for I and j. So we can create one big two-dimensional array for I and j and just store the solution for RMQ there. So the query is one array lookup, well, maybe in a two-dimensional array, but you can even map this to a 1D array if you wanted. So we can compute every individual answer in linear time. There's n squared answers. That gives us a cubic pre-processing time, but constant query. It's probably not good enough to be interesting, but at least it shows what is possible at the extreme ends. A simple observation is that we can get the pre-processing time to quadratic, so filling the array in constant time. And you can do this because if you have your current range I to j, you can take one element off, the last say, and then what is the possibility for the range min query in I to j? You can find where the range min is if you leave out the j, and that's maybe here. So then RMQ ij is either RMQ I up to j minus 1. This you cannot see. It's either RMQ or the result is j. And these are two different options. So you can take constant time to compare the values at that position and then insert into your array m, whichever was the smaller one. So by filling the array in a somewhat smart order, going from those with a small range to those with a bigger range, is enough to get this result: quadratic pre-processing time, constant query time. That's what you can easily do. Unfortunately, this is still far away from our ultimate goal of a linear pre-processing time, and we will continue tomorrow with our quest towards this goal. Thanks. That's all for today. I would have a quick time for a social if someone wants to join on Zoom. Not a ton of time, but 10 minutes is definitely fine. Otherwise, see you tomorrow. Think about the programming puzzle. Please have a look at the website and read through the instructions if you haven't done so. Make sure to familiarize yourself with the task so that we can have a little bit of a discussion about this tomorrow. If enough people are reasonably familiar with it, maybe we can see if I can provide a little hint for this one, or if we don't need that. See you tomorrow, same slot, same time, or in 2 minutes on Zoom. Bye for now.